new guy. Good morning. Thanks for being here. So I will try to talk about something else, although it's quite similar to the first one, in fact. So this work is related to a Marie Curie research innovation staff exchange program we are involved in, and it is led by a Greek university at Athens, and we have several partners in the consortium, and we have academics. That is a Spanish institute on games, on all games, IJU, and ourselves. And we have two companies, Spanish company that has expertise in vision-based application or graphic visualization and so on, and Stream Vision, which has interest in telemedicine. So Prophetic is a project that aims to develop a innovative or new personal health system for Parkinson's disease. Parkinson's disease is a progressive movement disorder, and there is no clear therapy for Parkinson's disease. And the disease is characterized by movement disorders such as muscle rigidity, tremor, slowiness, freezing of gait, and so on, and also some cognitive impact. So the idea is to use ICT techniques to try to monitor the health status of individuals, and also to develop techniques to maintain their motor abilities. So in the project, we plan to, we are thinking about developing a Kinect-based serious game to maintain motor control performance, and also use body sensors for remote monitoring that can be used by health provider and so on. Okay, so hence the talk. The talk is about how to exploit how to use the body sensors that are developed within the consortium by Stream Vision company, and to recover the orientation, the motion, and so on. So this boils down to the problem of attitude estimation. So the attitude of an object is the orientation of a body, and one way to characterize the attitude is to compute the rotational matrix between a fixed frame, a navigation frame, and the body frame, that is a frame that is attached to the body. There are many ways to do this. One convenient way is to use the quaternions, and specifically the subclass of orientation quaternions. These are unitary four-dimensional vectors. You can think of them as a generalization of complex numbers, or they have nice properties, and in particular regarding rotations, there are no singularity. Any rotation between two vectors in the body frame and between body frame and navigation frame can be conveniently characterized by a rotation matrix. It is here, the direction cosine matrix that is related to the quaternions. Okay. This is quite classical technique. You can find the details on it in any textbook. The kinematics of a quaternion is also characterized, and what is interesting is that the kinematics is a linear equation, provided you know the angular the angular change rate or the angular velocities over the several axes. So the angular, I'll consider here the sensor, the body of the sensor. So there is a frame attached to the body of the sensor, and the sensor includes several modalities. Let me talk about gyrometers. So that give the 3-axis angular rotational speed. So the sensor is able to measure the rotational speed around the axis. Okay. So provided this rotational speed vector is available, the differential equation is linear. The expression of this matrix includes rotational cross matrix and so on. So it's well defined, kind of vectorial project matrix rewritten as or cross product rewritten as a rotational matrix. Okay, so as I said, 3 modalities. The third one is the gyrometers. So the first one on this list is accelerometers. So these accelerometers, there are several techniques that can do this, but I will not go to detail about the technology, but they provide the projection of the total acceleration of the body onto the axis of the body. So they can be used to recover the horizontal plane, provided there is no inner or translational acceleration. The same thing with magnetometers. They can project the magnetic field vector onto the body axis, and since the orientation of the magnetic field is known, you can recover also. You have another modality to recover the plane and the north in particular. So these are the output equations. So the measurement equation relates the measured data, which is something proportional to acceleration. Also, they are denoted as force, but these are acceleration. And this is the projection of the total acceleration. So gravity plus the translational acceleration of the body. So this is an issue, in fact, because if we use accelerometer just to recover the tilt angle, if you have inner acceleration, if you have translational acceleration, you have a disturbance. So this is an issue I will talk later about it. So and then this is the direction cosine matrix related to the state variable, which is the quaternion, and the quaternion or this matrix relates the orientation of the body with respect to the navigational frame. Okay, so classical equation, linear with respect to the physical entity we want, but very, very non-linear, strongly non-linear with respect to the state variable. So difficulty is here, is in the observation equations. The magnetic field has a known tilt angle, so it's no big deal. Although it's uncertain, but it's well documented. That is, it is uncertain. And as I just recall here, the rotational speed is measured. Okay, maybe a comment about the quaternion space. So in quaternion space is not a Euclidean space. So so definition of error is something that is delicate. And to define an error in a quaternion space, we should use the idea of rotation. So an error in variables that characterize a rotation is a rotation itself. So the error quaternion is a combination of a rotation and an inverse and reciprocal rotation. Hence the notation and the definition of the rotation of multiplication of 2 quaternions. So this is tricky, and it's not something important to keep in mind, and this may have some consequences in the analysis. Okay, so is there any difficulty to apply interval analysis on these type of equations? So the answer is is no difficulty if you want over approximation, very difficult to have inner approximation, but still, there is no mathematical definition, difficulty for over approximation. There is a experimental difficulty. Problem is that the measurements are sensitive to disturbances, and it's very difficult to use the state-of-the-art state estimation techniques based on interval analysis. So maybe we could take benefit from what is done in the literature. There are two origins, two sources of disturbances. The first one is, as I said, the translational motion accelerations and magnetic disturbance that are perturbing the measurements of accelerometers and magnetometers. And there are bias and drifts in the gyrometers that computes the angular velocity. Typically, when you put a sensor on a table, it's a static mode, and the sensor is still measuring a rotation. There is a bias and a drift in the measurement. And acceleration, of course, will perturb the measurement. So what is interesting is that the disturbances acting on accelerometers and magnetometers are acting on high frequency range, because these are rapid signals. And in fact, we want to use accelerometers and magnetometers to have orientations and tilts. So we are looking for information that are low frequency range. So it would be easy to use a low pass on these signals to get rid of the perturbation. And then bias and drifts in gyrometers are low frequency signals, so we could use a high pass to get rid of this drift. Okay, so there is in the literature an approach that is 10 years ago now, more than 10 years old. The idea is to use what is called a complementary filtering approach, because you use two filters. For instance, here, first order. Think about applicability and embedding this computation in a sensor. So simple filtering. Low pass, high pass, they are complementary. The sum is equal to 1. Okay, and you apply this to accelerometers and magnetometers, and this to the gyrometers, and you can relate the parameter k to the crossover frequency. But of course, the problem of tuning k is an open problem, so it's not that easy. But this way of doing has shown some results. So the idea is to combine this with interval analysis. I mean, to first filter the data before applying interval analysis techniques. Okay, so we just use classical unknown bounded error approach, as I said earlier. One thing which is interesting is that the angular velocity is available. So we can, for instance, assume that we have an idea of all the velocities over a window time frame, a time step, for instance, between two measurements. We can assume that the angular velocity is interpolation of the two, whatever. Voilà, that's an assumption. And if we do this, we can then directly use Picard theorem, Picard-Lindlof operator, and to compute the reachable set for the quaternions, starting from one step ahead reachable set for the quaternions. And hence the problem, which was continuous time, becomes discrete time. And then we can use classical techniques as defined by Michel Kiefer, for instance, just to recall. The idea is to do forward computation, and then you have the correction as already said. In the second version step that will remain, we use the CVA, but we have used a dedicated interval contractor. I mean that all the nonlinear equations, we have written down the contractors specifically for the problem. At that time, So it's optimal for this problem. Before applying them, we have one last issue to solve, is the remaining disturbances. So the measurements are normalized. The acceleration and the magnetometers are normalized in the sense that their norm should be equal to 1. So we can check by the measurement if there is a strong disturbance or not, if the norm differs from 1. It means that there is disturbance. So we have adapted the output, the feasible domain for the outputs to take into account the disturbance that is measured. If there is a strong disturbance that is detected, then the feasible domain for output is increased. Sometimes the solution set is empty, therefore, because there is so many disturbance and we cannot manage, so the solution set is empty. Hence, we do reset. We just forget about the past and we start from the whole set of quaternion. And we also detect the static mode when the angular velocity goes below a given threshold. We say, okay, it's static mode, and we stop. We froze the estimation. So doing so, we managed to obtain some results, quite noisy results, in fact, because the data is also very, it's a very dynamic situation, and the purple curves are the bounds of the feasible domains for the quaternion. The red one is the midpoint, and the blue are the true quaternions. You can see sometimes the bounds that just goes to 0 to 1, which is infinity. I mean, it's all there is nothing we can do there because we have detected inconsistency. So we got rid of the past value. So there are too many problems there. So there is still work to do. Another kind of results for the other variable number 2, Q2, the component number 2 of the quaternion, we have similar results, and you can see that. So it's not that easy to apply interval methods on quaternions or on data that are subject to strong disturbances. So there is a need for strong filtering, signal processing techniques prior to use the interval analysis. So the application of interval analysis in attitude estimation with true data is something up to now have only mixed results. I'm not that satisfied about the outcomes, but still there are interesting problems to address. The first one is theoretical issues, because we are on a non-Euclidean manifold, and so we have to be careful about the definition of the error, as I mentioned. So this has not been exploited yet. There is also another difficulty, is that we are working on a solution set, which is the unit quaternion. And this unit quaternion, there is a constraint on this unit quaternion, and this constraint corresponds to a domain of 0 volume. So if you have a solution set that is in a 0 volume set, you cannot compute inner approximation. So we have to think about changing representation. Okay, so there is an issue, theoretical issue there. One other observation is that maybe pure bounded error approximation or error assumption for the error is not adapted. Maybe we should consider a probabilistic distribution on the errors, but bounded uncertainty in the models, in the measurement model. Hence, mixed uncertainties should be the next theoretical step. On the implementation aspect, measurement is done every 5 milliseconds, no, 50 milliseconds. So it's 10 times faster than our computational capability at each step. So our algorithm cannot be used online. And then, of course, experimental issues, as I mentioned. Thank you.
Any question? Yes.
Good question. But for this application, is it important to have a bounded solution? Is it worth using intervals? So do we need like a solution that is bounded?
For this application?
Yeah. So it's like more like a theoretical work.
Yes,
or
yes.
Do we really need a bounded solution for opacity? So
For the application, we do not need such kind of theory, yes, but it's a theoretical work that has been initiated thanks to the reflection about this, the thoughts about this kind of applications as a general, yes. But in situations such as autonomous vehicle or autonomous drones and so on, UAVs, and having an idea about the robustness of the solution is may be interesting, yes.
yeah, I got the same problem. I work on biomedical applications. I would love sometimes to use intervals, but I ask myself, do I need them?
Yes, yes, yes. Maybe there is one detail that would be interesting, because although yes, you're right. It's really a theoretical consideration, because this is not a critical safety critical application. But in safety critical application, I think interval analysis can be interesting for attitude estimation, for instance, if we consider the errors in the measurement model, because the sensors are assumed to be perfectly orthogonal, which is not true. So you have a kind of modeling error in the model uncertainty in the measurement equations, and it can be interesting to plug some intervals there. Yes.
Oh, you have a question? Yeah.
The question that is linked to the previous one, I think, have you a comparison in terms of robustness and accuracy with some probabilistic estimators such as, nonlinear probabilistic estimators such as unscented Kalman filters or particle filters?
Yeah, not yet, but we are planning to go forward in comparing with unscented Kalman, with extended Kalman filter. It would be easy to do unscented, but maybe box particle filter. I will try to work with you, then ask you a question. We can compare results. That would be nice.
Okay. So I have some question about the inner approximation.
Yes.
Probably you don't have to deal with quaternion, but more because with the quaternion you will have you are in R4.
Yes.
You have a 4. And the orientation is a three-dimensional manifold. So probably it would be better to work with Euler angle. You could have an inner approximation, but with quaternion, I don't understand how it could be, because you are
yes.
there.
That's my comment. I mean,
yeah, so maybe with Euler angle, you
yes.
could, but I understand.
Because the quaternion has nice theoretical properties, and I mean on the equation the dynamics are linear, and and also there is no singularity in the.
And another problem I can see, but as far as I remember, if you have one orientation, you have two possible quaternions.
Yes, yes. So hence we filtered one of the components is positive. There is a constraint. Yes.
In this case, if you do such a constraint, your manifold will have borders. So
yes.
maybe you would jump from one border to another. Maybe you may have some problems.
Okay, I haven't thought about that.
Oh, okay. So okay. Any other question? So that's perfect, because we have more time for coffee.
Yeah. Thanks.